input resistance, or we call it in biomedical instrumentation, we call it more general as input impedance, yeah, because later in next semester you will learn about capacitance, so capacitance, inductance, and resistance. And it is very rare that we have only pure resistance in a component or in even in a wire. So that is why that usually it will have also capacitance. By the way, can you see the the slide or not?
Yes, we can.
Yes. Okay. Wait. Now, can you see it?
Yes, sir, we can.
But I think okay, this one. Okay. So input impedance and then has also voltage dependent voltage amplifier and then the output impedance as well. This is the output impedance. The RO here is the output impedance. So in this current chapter, we only assume that it has only resistance. That's why we call it in output resistance. But similar with input impedance, later also in next session, next semester, we will learn about impedance. So actually, it has also capacitance component, inductance, maybe also inductance component that we call it in general as output impedance. Okay, input resistance, output resistance, and the gain. And these are the typical values in off-the-shelf operational amplifiers. Yeah. Then we have learned last week also continued with yesterday, no, the day before yesterday on several circuits, yeah, with operational amplifier, the model, and then the driving circuit, and then the load, and then the op-amp itself. So whenever you are modeling a circuit containing op-amp, you can always cut the op-amp part and then replace it with this resembling linear circuit model, okay, to analyze it further. Then you can analyze it using PSpice, circuit analysis software, etc. Although now most of the PSpice software, they already contain op-amp as their basic components. This is the transfer plot for some commercial op-amps that we have also learned. The saturation region. So as a rule of thumb, that usually the amplification, the output, should not be beyond the values of the driving voltage, yeah, the VCC and the VEE. Yeah, so later we had learned also the day before yesterday, when it reaches beyond the values of the driving or power supply voltage, then it will saturate, like this one. Then we had learned about buffer or unity gain buffer or voltage follower of a negative feedback, yeah? Negative feedback operational amplifier whose function is to amplify with one gain. What the gain is one. Basically, the purpose is to maintain the voltage value. Okay, and we had discussed about the model also, deriving the V output over V source. And then we have learned last week about ideal operational amplifier model, with which we can analyze op-amp containing circuits simpler, yeah, with much simpler assumption. So using the ideal op-amp, then the analysis could be made simpler. So the ideal op-amp states that the input impedance or input resistance is infinity, output impedance is zero or circuit, then the gain is infinity. So the infinite input impedance will imply that there is no input currents to the terminals of the operational amplifier. So both currents at the inverting and non-inverting terminal will be equal to 0. Infinity gain will imply that the voltage, the V plus is equal to V minus, because V plus minus V minus will be almost 0. Okay, so in order that there is V output, the A has to be infinity. So we have also tried to analyze the unity gain buffer using ideal op-amp assumption, and we have also compared the result with linear op-amp model, and then found out that using ideal op-amp model, we can approximate the result using the actual linear circuit model. Okay, then we learned some example last week as well as the day before yesterday. This is this is an inverting amplifier as well. So inverting amplifier means like this, yeah. The V output sign will be opposite of the source voltage sign, so because of this negative amplification, because the input is inserted into the inverting terminal, the negative terminal. Okay, and we have compared using linear circuit model like this, yeah, replacing the op-amp symbol with the linear model with input resistance, output resistance, and gain amplifier, and then analyzing using node analysis. Okay, and we have obtained the linear circuit model, which is quite complex. However, the result will be basically almost similar with the result of that is obtained using the ideal op-amp model. So basically, in this chapter as well as most of the uh, quick analysis of circuit having an op-amp, usually we use ideal op-amp model. Only when we are required to have a more accurate, more precise number of the output of certain current or voltage, then we will use the linear circuit model and then put into, for example, SPICE software to analyze and calculate that values. Okay, so this is the summary, comparison of ideal op-amp and non-ideal case. Then we learn some examples, yeah, using ideal model as well as linear model. This is a differential amplifier where the voltage is the amplifications of the difference between the input to the non-inverting and inverting terminal. Yeah, the V plus minus V minus. This is the differential amplifier. This is when we analyze using ideal op-amp condition. Okay. Then yeah, this is the same. And this is also another example of finding the current here at the load, this 10 kilo ohm load, using the ideal op-amp approximation. This non-inverting amplifier example also analyzed using ideal op-amp amplifier. So in non-inverting, the voltage input is inserted into the non-inverting terminal, the V plus terminal. Okay, so here we have learned the day before yesterday, also last week, that the output can be calculated using an inverse voltage divider formula. Yeah, when we use ideal op-amp approximation. When we use non-ideal op-amp linear circuit model, it will be a little bit complex, something like this. Okay, and then we will obtain the gain. In this case, yeah, we have to analyze the matrix, determinant, and adjoint, and then finding the output over Vs. The output. So when V output divided by V1, this is the value, yeah, this and this. When we use ideal op-amp, the gain A will reach or will approach infinity, yeah, the input resistance also approach infinity, and the gain will be similar to ideal op-amp approximation. Then the day before yesterday, we have also learned about semi-ideal op-amp model. Yeah, this is when we do not assume that the gain is infinite. So we still use the uh, the gain provided by that component, by the manufacturer. What we approximate is the impedance or the resistance. The input resistance is approximated as infinity. Output resistance is approximated as short circuit, yeah, or zero. These conditions are similar with those of the ideal op-amp model. Okay. So as a result, since the gain has a value, so V plus will not be the same as V minus. So we have to replace the equation with V output equals to this AO times the difference between V plus and V minus. Okay, so this is the semi-ideal op-amp model. The input impedance is infinity, so that's why it is open circuit, and output impedance is zero, that's why it is short circuited, yeah, to this output. So using semi-ideal model, this is what we have. So there is another factor called as beta besides the AO. So the V output over Vs will be equals to the AO divided by 1 plus AO plus times beta. Yeah. So so beta here is basically the same as the amplification when it is ideal model. Yeah, for this case, this is a non-inverting amplifier. So VE will be the actual gain minus the ideal gain divided by the actual gain, and this equals to 1 over 1 plus AO beta. Then we have learned some problems 2 days ago, okay, using the infinite gain assumption. So means this is ideal op-amp approximation. Okay, for this circuit, this is basically a negative feedback circuit, yeah, or differential amplifier circuit. Then, yeah, draw the linear equivalent circuit and write the loop equation. So this is also, I believe, we have done it just 2 days ago. Okay, so replacing it with the linear circuit model, and then using loop method or mesh method, yeah, to find the V output VO. This is the same. I think we have done it 2 days ago, the day before yesterday. Yeah. And this is also something which we had done 2 days ago. So we are given design criteria. For example, if the supply, if the input here V1 is between 1 volt and 2 volt, and the V2 is between 2 volt and 3 volt, yeah, DC supplies are plus minus 10 volt. We are asked to find if both circuit fulfill this condition. V output equals to 8 V1 minus 4 V2. So basically this is a differential amplifier having the inputs being amplified with different gain. Okay. Determine if both implementation produce the full range for the output. So in this case, first we derive this. So usually when we have a blocks, yeah, or blocks of op-amp circuit, yeah, we studied block by block. Yeah, like this, we derive first the output from the first op-amp is Vx. So Vx here will be equals to V1 minus V2. Yeah, how is it derived? This is using the positive. This is the inverting amplifier. Yeah, inverting amplifier here. So if V1 here equals between 1 volt and 2 volt, and V2 between 2 volt and 3 volt, if we put here, yeah, so we have to find the lower limit and then the upper limit of the Vx, right? So here then we put the smallest, which is V1 minus V2. So the smallest difference here will be when V1 is at its smallest value and V2 is at its largest value. So we insert V1 equals to 1, which is 2. We insert V2 equals to 3 here. 2 minus 3 equals to minus 1. So we will obtain the lower limit, yeah, of this value of Vx. Then the upper limit is when the difference is big, the biggest. So it is obtained when V1 is at its highest value and V2 is at its lowest value. Okay, so the value of Vx will be 2 times 2, 4 minus 2. Yeah, 4 minus 2 is 2 volt. So here the value of Vx is between minus 1 volt and 2 volt, which is still within the limit of the DC supplies plus minus 10 volt. That's why it is not saturating. Okay, so because the question is determined if both implementation produce the full range for the output. So Vx is okay. Now calculating here, V output here, this is a non-inverting amplifier, yeah, whose value here is V output will be equals to 3 divided by 3 plus 10, right? 30 kilo ohm divided by 30 kilo ohm plus 10 kilo ohm, or 4. Yeah, this is a non-inverting with using inverse voltage divider formula. Okay, yes. So 30 kilo ohm plus 10 kilo ohm divided by 10 kilo ohm. Okay? So it will be equals to 4. The output for Vx. So when we multiply with 4 here, the lower limit will become minus 4. The upper limit becomes 8 volt. So this is also still okay because it is still within the DC supplies plus minus 10 volt. So it does not saturate the operational amplifier. Okay, so now we analyze the second circuit. Vy here equals to negative 8 volt. Okay, this is an inverting amplifier because with the feedback 8, yeah, 8 times the V1. That is why negative Vy. So it means when V1 values is between 1 and 2 volt here, the values of Vy becomes minus 8 until minus 16. So between minus 16 volt to minus 8 volt. Now, this is already below the negative power supply, which is minus 10 volt, right? So it means the output Vy will already saturated. So exceed the supply value, this op-amp will saturate. So the second circuit is a poor implementation to obtain this condition. Yeah. So this is how you analyze the design criteria. The day before yesterday, 2 days ago, we have also learned about comparator circuit made from this similar like differential amplifier, okay, but without any feedback. Okay, so here when without any feedback from the V out to the negative terminal or non-positive terminal. So here the V output will produce VCC or the positive power supply when V plus is larger than V minus. Okay, and the V output will be equals to VEE, the negative power supply, when V plus is the V plus here is smaller than V minus. So when we put this here, when we put the V minus here to be 0, we grounded the V minus, so the V source will be compared with 0 voltage, and then we will obtain what we call as the zero crossing detector. So in this case, the VCC is put in with a load resistor here, so not to the value, the output will not be VCC itself, but will be 5 volt. Yeah? Oh, okay, this is the VCC value, and the current will be limited by this 3 kilo ohm to this output. So whenever the sinusoidal, if this is the V source is an alternating current, which you will learn next semester, then there is a positive and negative regions, right, of the values of that signal. So whenever it is positive, then the output of the op-amp will be positive, which is the VCC value. Whenever it is negative, it will be VEE here, minus 5 volt. Okay. So what if we don't want it to be VCC and VEE? We want it to be another value, voltage. It will be a good question. So you need to design something like to drop the voltage here. Okay, between VCC, voltage divider maybe one, so that then you don't probe directly this from the VCC, but rather you probe from the division, the voltage division. This is what we call as a pull-up resistor. And we have learned also 2 days ago how to sense or to detect current, and converted it into voltage using operational amplifier. Okay, so the current is put into a resistor, so it becomes a voltage input, right? And then we amplify this input voltage using a negative non-inverting amplifier like this, because the input is connected to the non-inverting terminal of the operational amplifier. The feedback is this in the inverting terminal and grounded, and then you feed the output voltage. Okay, so in this case, the gain will be 1 plus R2 over R1. Any questions so far? Summarizing what we have learned on operational amplifier. Quite clear, yeah, everyone? Seems to be no feedback.
No question, sir.
Huh?
So far, no question.
No question. If no feedback, should we have a surprise quiz?
No, sir, I have answered.
Okay, yeah. So then the V output will be gain times the V input here. The gain is the form, is basically an inverse voltage divider formula. 1 plus R2 over R1. Okay, so we have also revisited this 2 days ago. Okay, with using non-inverting amplifier to amplify the input from the driving voltage to the motor. Okay, using this operational amplifier, non-inverting amplifier also, whose gain is 1 plus RB over RA. And the design is, it should be 4, the gain should be 4. So here RB over RA will be equal to 3. Yeah. The constraint is that the motor voltage should be less than 20 volt, and the power dissipation in this amplifier should be less than or equal to 100 milliwatt. So by using the simplified assumption, the ideal model, which is the input resistance should be approaching infinity, output resistance is approaching 0. So the significant loss will only occur through this RB and RA, not inside the op-amp. Yeah. So when PM here equals to 20 volt, so the PX here will be then VM here is already 20 volt, means here VM should be the maximum value of VM. The power, the maximum power will be 20 volt square divided by RA plus RB, right? The combination of these two resistors. And this should be less than the maximum allowed power dissipation, which should be less than 100 milliwatts. So from here, we obtain the value RA plus RB should be larger than this one is 4,000 divided by 100 milliwatt, or 0. This is 4,000. This is divided by 0.1 watt. 400. Sorry, this is 400. 400 divided by 0.1 watt, so equals to 4,000 ohm. So RA plus RB should be larger than or equal to 4,000 ohm. The value, at least RA plus RB should be 4 kilo ohm. Then the second criteria from the design equation, if you use non-inverting amplifier, so RB divided by RA should be equal to 3, and then we can insert it into here, for example. So RB equals to 3 RA, so 3 RA plus RA becomes 4 RA should be larger than 4000 ohm. So RA should be 1 kilo ohm at least. So RB will be 3 kilo ohm. And this is the standard values at 5%. If we want to be safer, then you put more RA. So for example, 1.5 kilo ohm, then RB will be 4.5 kilo ohm, of which then the total value RA plus RB will be 6 kilo ohm, much larger than 4000. So it means then the power dissipation will be less than 100 milliwatt, much lesser than 100 milliwatt. Safer in terms that it will not exceed that maximum power. Okay, but of course then the drawback will be that your DC motor cannot rotate as quick as when it is 100 milliwatt. So this 100 milliwatt, when your motor is operated at this 100 milliwatt, it will rotate, it will spin at its highest speed. But the danger is when it just exceeds a little bit. So for example, the 5%, the value here is less than 1 kilo ohm, for example. So this means will be less than 4000. This sum will be less than 4 kilo ohm. Then the power dissipation maybe will be larger than 100 milliwatt. So the motor may overheat and maybe will burn, right? Will fail. So this is something then you as engineer has to design. You have to incorporate all this design criteria when you design an application, an instrument. Like this is basically an actuating instrument with a motor. So the design criteria in this case that you want to speed up the motor, however, should be within its limit so that it will not overheat, it will not burn. Okay. Okay, so this is something new which we haven't discussed 2 days ago. So this is another design example called as an instrumentation amplifier. An instrumentation amplifier now usually is already sold as one single IC component, integrated circuit component. It contains multiple operational amplifier circuit within it. It contains one differential amplifier, and before the input is inserted into the differential amplifier terminals, each of the input is being amplified using a separate operational amplifiers here. So for example, here we have V1 input and V2, each of input to the first, V1 is input to the first operational amplifier, with non-inverting configuration, right? V2 is similar, also non-inverting configuration. So in this case, then the gain here will be how much? R plus R2 divided by R. In this case will be R plus R1 divided by R, right? So this is the supply, this 3-volt supply, okay, which can be made from 2 series 1.5-volt batteries. And then this will be the amplified V1, which becomes Vx, inserted into the non-inverting terminal of the third non-operational amplifier using this configuration. Okay, so what will happen is this is a differential amplifier basically. So the output here will be the difference between Vx and Vy. Okay, so this Rb is made to be the same as Ra. So these 4 resistors are the same. Okay, we can derive. So this is already derived, I think, in several slides ago, which is the differential amplifier. So the design specification is that the gain, the V output, should be 10. 10 times of the difference between V1 and V2. Okay, that's why gain equals to V output divided by V1 minus V2 equals to 10. So this is instrumentation amplifier. Okay, of course, in differential amplifier, it is also amplifying, but this one is before it is being inputted to the differential amplifier, it is pre-amplified using the this non-inverting amplifier, each of the inputs. So an instrumentation amplifier has high input resistance, or high impedance, input impedance, low power dissipation, and operate from 2 AA batteries here. This is what is important. Yeah, because when and this circuit is commonly used in biomedical instrumentation. Why? We do not want to draw any current from the signal source, because when we draw the current from the signal source, it means that there will be power loss. Information will be lost. Okay, so that is why our amplifier should have a high input impedance or high input resistance in this case, yeah, because we haven't learned about impedance yet in this semester. So that then when it has a high input impedance, it will not draw current. Remember the ideal op-amp approximation, because it has um, infinite input resistance, there is no current being drawn towards the op-amp. The current at both terminal are zero. Okay. So analysis of this proposed configuration. Yeah. So let's analyze this one. This is V output equals to this is Vx minus Vy. Okay. So here Va equals to V1. Yeah, because they are using ideal op-amp approximation. Vb equals V2 here. Yeah, Vb here equals to V2. Then at this node at A, so V1 minus V2 here divided by R plus V1 minus Vx divided by R1 equals to 0. Here at B, V2 minus V1 divided by R plus V2 minus Vy divided by R2 equals to 0. No current, yeah, no current flowing through this terminal because of the ideal op-amp approximation. And V output here equals to Vx minus Vy. This is from the differential amplifier equation. Okay, you can derive it if you want. We have derived it in some slides earlier. So from here, then V output equals to Vx. We replace with this value from here, yeah, which is V1 multiplied by 1 plus R1, yeah, R1 over R, or basically R plus R1 divided by R negative, yeah, V2 here, the Vy equals to this part, yeah, V2 multiplied by R2 plus R divided by R, so 1 plus R2 over R. Then plus V1 R2 over R minus V2 R1 over R, okay, minus V2 R1 over R. Then we simplify the design by making R1 equal R2. If R1 equal R2 here, so this is, let's say, R1, then we can simplify further. So this becomes 1 plus 2 R1 over R. 1 plus 2 R1 over R multiplied by V1 minus V2. So this will be the gain. So this is larger than the normal non-inverting amplifier, right? Because of this factor 2 to R1 over R. Now the design equation is this one. The gain 2R1 equals to 9R. 2R1 equals to 9R. Why? The gain here is supposed to be 10, right? So this value is 10. What is it? This one, yeah, 10. So 10. So 2R1 over R equals to 10 minus 1, minus 1. And that's why 2R1 equals to 9R. This is the value, okay? Then from here, use large resistor for low power. And this is the resistor. Wait, he just came. So from here, use the large resistor for low power. Yeah, for R, 100 kilo ohm. Why we use large resistor for low power? Yeah, when the resistors are large, the current being drawn is small. Okay, I square R. Yeah, the formula for power is I square times R. So when the resistor and when the resistance is large, current I equals to the voltage divided by R. When the resistor is large, the current will be small. So the current will be, the power also will be small. So if we use the R here to be 100 kilo ohm, okay, so we will get R1 equals to 4.5 times 100 kilo ohm. Yeah, R1 and R2 equals to R2 450 kilo ohm. Okay, so this is, for example, is max 4240. One example of operational amplifier. Okay, it's clear now the drawing. Okay, let's do some of this design example. Again, this is a what? Non-inverting amplifier. Yeah? The design specification now is that V output divided by V in should be equal to 10. Power loss in resistor should not exceed 100 milliwatt. Okay, when the V in itself, the range of the V in could be from minus 2 volt until positive 2 volt. Okay, what should we do? So from here we obtain the equation V output over V in, the gain equals to 1 over R2 divided by R1, right? Or R2 over R1 plus R2 over R1. Okay. This is non-inverting amplifier equation. So here equals, this should be equal to 10 according to the design specification. It means R2 over R1 should be equals to 9, right? And here the maximum V output is 20 volt. Okay. So yeah, from the VCC, I think this is from the VCC specification, the supply, DC power supplies. So the power due to this R1 plus R2, the dissipated power from the R2 and R1 should be less than so should not exceed 100 milliwatt, right? So V square divided by the R, so 20 volt square divided by R1 plus R2. So it should be equals to 100 milliwatt. So the power should be less than this. So this should be less than 100 milliwatt. Okay, so we solve the design equations. Let's say, so here from here means that R2 equals to 9 R1. R1 plus R2 here should be larger than 4 kilo ohm. Yeah, similar like the previous slide method. So it means R1, this value should be less than or equal to 100 milliwatt. Okay, so R1 plus R2 should be larger than this 400 divided by 100 milliwatt. 100 milliwatt is 0.1 watt. So this becomes 4 kilo ohm. Yeah, 400 divided by 0.1 is 4,000. Yeah, 4,000 ohm. So be careful with the units here because this is milli. So if you convert into watt, yeah, because this is volt, yeah, to obtain ohm, you have to use convert this into 0.1 watt. So R1 plus R2 should be larger than 4 kilo ohm. Okay, and if we choose R1 to be larger than or equal to 400 ohm here, so then R2 will be 9 times R1, yeah, 3.6 kilo ohm, right? 3.6 kilo ohm. So we obtain that R1 plus R2 equals to 4 kilo ohm, yeah, at the limit. So this is how we solve design criteria. So there is a criteria from the gain itself, which we want to obtain, and there is a criteria also from the power. There should not be too much power loss in the resistor. Yeah. Another example, implement the operation V output equals to minus 0.1, 0.9 V1 minus 0.1 V2. The design constraints, as few components as possible, minimize power dissipated, and use resistors no larger than 10 kilo ohm. Okay, the resistor should be no larger than 10 kilo ohm. So one way, this is, if like this, then usually you need to design a differential amplifier, right? So this is one configuration. This is basically the voltage applied here will be equals to the voltage here negative minus the voltage here with a factor from R over R1. This is not a differential amplifier by itself. This is basically an inverting amplifier. However, the input is also amplified according to the ratio R over R1 and R over R2. Okay. So this is a weighted sum with sign change, which is basically an adder circuit, an adder optane circuit. Okay. So analysis of the circuit at this node, yeah, V plus equals to 0 because it is 0, right? Here it is grounded, so this why V minus is also 0 using ideal op-amp approximation. So at this node, yeah, basically this is a single node, right? This is a single node. This is they are connected, and here V this node there minus V output, and this is 0, right? So 0 minus V output divided by R. Then here plus 0 minus V1, so minus V1 divided by R1 plus 0 minus V2 divided by R2 equals to 0. So from here, then we obtain that V output. We move this term to the right hand side, or this, yeah, to the right hand side become V output divided by R. So then the multiply both sides with R. So V output will be equals to minus R over R1 V1 minus R over R2 V2. This value. So here we can get it. Yeah? We can approximate this. So R over R1 should be 0.9 and R over R2 should be 0.1. Okay. Yes. So from there, let's just try it. So from here, R over R1 should be equals to 0.9, right? And R over R2 should be equals to 0.1. Yeah. So R1 over R2. So which means then this R equals to 0.9 R1. So we replace R here with this value. So then 0.9 R1 divided by R2 equals to 0.1. Okay, so this becomes 9. This becomes 1. Yeah, so 9 R1 equals to R2. This is this equation. Okay, understand now? So use resistors no larger than 10 kilo ohm. Okay, this criteria. So using from here, from this criteria, we know, so R2 will be the largest value and R will be the smallest because R is 0.1 R2 while R1 is 1 over 9. So R2 1 over 9 of R2. So R2 1 over 9 is about 0.111, yeah. So R1 is a little bit larger than R, right? So R2 is larger than R1, R1 is larger than R. So solving the design equation by trial and error. For example, if we can choose R2 to be either 10K, 5.6K, yeah. Then we can obtain the value of R. R1, yeah, R2 divided by 9, we obtain R1. R2, so to obtain R, we multiply R2 by 0.1 or R2 divided by 10. Okay, so then we need to analyze this whether that component, each of those components are available as standard component. Okay, if it is not, then maybe then we have to combine several components of resistors to become with using series or using parallel, so that then they become what do you call it? That values. Yeah. Okay. Let me first clear the drawing. I think this is. Let us finish this slide, yeah, so that then we can conclude the first session. This is the another design example. I think the slide just few more. Design 4 to 50 milliampere to 0 to 5 volt converter. So this is like in the one of the previous slides, we see a current to voltage converter. So this is basically that thing. Yeah. So this is useful when you want to design an amplifier or a secondary transducer from a sensor, reading the sensor output when the sensor output is in the form of current, for example, like coil, coil or inductor, the output is current, then you convert it into voltage. Or you see 4 to 20 milliampere is basically the not in industrial instrumentation. It is the value of the current to represent the reading of a sensor. But usually now the processor and the controller uses voltage as the value. So you have to convert first the current into converter. 4 to 20 milliampere, you have to convert into range of 0 to 5 volt. Yeah. So how to do so? So convert the current to voltage using a resistor like this, right? Similar like the previous slide. So you, when flowing this the current into this resistor, then you obtain the voltage across this resistor. Okay, V1 equals to R times I. Cannot give the desired range because now you need to choose. The first is the initial resistor Vi. Now choose the resistor to provide the 5 voltage change and shift the level down. So for example, the resistor here will be the Vmax minus Vmin, the range of the between the maximum voltage output and minimum voltage output, which is 5 to minus 0, so 5 volt change over divided by the current range from maximum to minimum, which is 20 milliampere to 4 milliampere, 0.02 minus 0.004. So from here we obtain 312.5 ohm. Okay, and the V input range will then, when we put here, when it is 0.02 ampere or 20 milliampere, sorry, first is this one, the smallest one. When it is 4 milliampere, 4 times here, this value, 4 milliampere, the value will be 1.25 volt. Okay, so let's calculate. Yeah? Maybe I'm wrong. 4 milliampere or 0.004, yeah, times 312.5 ohm, then we obtain 1.25 volt. Then when the current is maximum, so when current is maximum, it is at 20 milliampere or 0.02 times the resistor value 312.5 is 6.25 volt. Okay, so what happened here? It is not yet according to the value we desire. Yeah, what we desire is from 0 to 5 volt, right? So we have to shift down. So putting an offset, negative offset, so subtract it with 1.25. So that this will become 0 and this becomes 5 volt. Okay, so what we can do is we have this differential amplifier with a shifter. Okay, this is differential amplifier. The voltage shift is provided by a voltage source V shift at this feedback. Okay. So here the P at the positive input terminal will be this is a voltage divider basically, right? This is a voltage divider from this. The value here is Vi, V input, and this is connected to the ground. Okay, so the voltage here, since there is no current flowing here, right? Because it is ideal op amp, so you can consider this is as disconnected. So this becomes a voltage divider. So the V plus here will be equal to R2 divided by R1 plus R2, V plus. Okay, then V minus here equals to this is also a voltage, basically a voltage divider, right, of the V output. However, since there is a voltage source here, so this is R1 over R1 plus R2, V plus minus V shift. Okay, This is voltage division plus this V shift. Okay. Then since V plus equals to V minus here, okay, because of the ideal op amp approximation, and when the gain is infinity, then this V plus equals to the V minus. This term equal to this. From there, if we derive further, if we simplify the equation, we will obtain V output equals to R2 over R1, yeah, times V1 minus V6. V1 minus V6. So here, then you have to find out then the value of R2 and R1. Yeah, R2 and R1. Okay, so here we deliberately set that this value R2 equals to this value resistor here, R1 equals to this value resistor here. So that then when we make them equal here, it can be simplified into this equation. So the V output range should be from 0 to 5. The input here should be between 1.25 to 6.25. The V output becomes 0 to 6.25. And then you have to find the value of R2 and R1. So you can set, for example, the V shift to be 1.25, yeah, 1.25, something like that. Okay, so this is a design example. So amplifier can be found in many instrumentation around us. This is one example in what do you call it? Sound system. Okay, where we have CD player, tape deck, phonograph. The sound is first after being recorded, yeah, from the CD or tape. You don't use CD anymore. Actually, now you use USB stick or even from the internet, right? Then re-amplifying it, yeah, and then using power amplifier to put the sound into the speaker, loudspeaker. So yeah, basically the amplifiers are made from operational amplifiers of amp circuits, yeah, like this. So this is a non-inverting amplifier. This is a unity gain follower, yeah, buffer, unity gain or buffer voltage follower. Okay. So determine R2 and R1 so that it provides an amplification of 1000, for example. Yeah, so then this is a non-inverting amplifier. This is the formula V output over V1. So let's say when V1 equals to 1, this is the unity gain amplifier, right? That's why this is the gain here, 1, multiplied to 1 plus R2 over R1. Yeah, so then you determine this R2, R1 based on the available component. But usually there is another criteria. The power output, the dissipated power should be less than 100 milliwatt, for example. Then that becomes the constraint, another constraint which you should consider to determine the R1 and R2 values. Okay, this is a sensor, yeah, a thermistor whose resistance value will depend on temperature. So RT, the value of that resistor equals to, this is an empirical value, 57.45 times exponent of minus 0.02270. Okay, and this is connected to a potentiometer Rx, usually to balance the resistor. Yeah, this is a non-inverting amplifier as well, or yeah, non-inverting amplifier. Then it is connected to this LED. The LED will, this is I think the comparator, yeah, display value depending on the values of the temperature, yeah, which is will determine the value of this RT here. Okay, so this is connected to okay, so this is a unity gain buffer, yeah, unity gain buffer whose input comes from this voltage divider, and we have here comparator circuit. So if the value Vt is above this reference value, this 1.4245, then it will set this on. Yeah, this is same, but this is less voltage. Yeah, etc. So when here is the temperature and the resistor string voltage. So when temperature increases, the Vt will increase as well. This Vt will increase. Okay. So this is the value, and this is the comparator output. The C1 here will be set when the value is less, yeah. But then this one, this voltage, because there is a voltage divider here, this will set only at lower, where when the Vt here is high enough, such that V2 can is high compared to this reference voltage. So that's why this LED, the LED2, LED3, LED4, and LED5 will be turned on when the temperature is high. Yeah, when the temperature is high, the Vt will be higher as well. The value at V2, V3, and V4 here will be also high. And depending on the threshold value here, because this voltage divider, it will set on the LED at this range of temperature. Okay, so this is how it looks like in the comparator outputs and the LED drive voltage. So LED 1 is on when temperature is low. LED 2 is on when temperature is between 65 to 70. LED 3 is set on between 70 and 75 degrees Fahrenheit. LED 4 between 75 to 80 Fahrenheit. Yeah, and okay, yeah. LED 5 is between when it is above 80 degrees Fahrenheit. So only one LED is on at any given time. At any given time can be only one. So when it is on at this period, then this will be off. Yeah, something like it. So this is the comparator circuit, a display of with a ladder of temperature. So we saw the sequence of MATLAB instruction used to obtain the plot of the voltage as a function of temperature. So this is the range, yeah, from 60 to 90 degree at 0.1 increment. The RT this is the model of the thermistor. This is the computed resistance needed for the voltage divider, yeah, voltage divider, the Rx. Then the Vt will be this 3 times Rx divided by Rx plus T. This is the voltage divider equations. Yeah, this is 3 volt here. The Rx over Rx plus RT. Okay. And this is the plot of the temperature as the x-axis and the Vt as the y-axis. Okay. This plot, okay, of Vt, output temperature sensor. Then when this is example when showing saturation when it is above the power supply. The output is above the power supply plus and minus 10 volt. So here the current here to the inverting terminal is 0, as well as the current towards the non-inverting terminal, and V plus equals to V1. Here because this V1 is this point, yeah, this V minus equals to V1, yeah, according to the op-amp approximation, yeah, the ideal op-amp approximation. So KCL at this node, V1 minus 0.5 over 1K plus V1 minus V output over 4K equals to 0. So from here we obtain V output equals to 5 V1 minus 2. Okay. So the transfer curve is when V1 is 2.4, 2 volt. 2 times 5 is 10, minus 2 is 8. So 2 volt, this is 8 value. But when it is 2.4, 2.4 times 5 is 12 volt. 12 volt minus 2 is 10. So when the voltage input is 2.4, the output value starts to be equal to the DC power supply. That's why then it is saturating. For example, let's set V1 equals to 3 volt. 3 times 5 is 15. 15 minus 2 is 3. Okay, 15 minus 2 is 13. Sorry, 13. So it will be saturated. So the output value will not be 13, but instead will be V output. Will be the same as this DC power supply. So if you would like to, so for it not to be saturating at 13, at V1 equals to V1 equals to 3 volt, then you have to have more of this this value, 2, which can be made by putting more higher bias here, for example. Okay. So this source creates the offset. Yeah. So because at V1 equals to 0, the value of the V output is minus 2. Yeah. The output cannot exceed the supply voltage plus 10 volt. Okay. Similarly here, the output cannot be below this offset, cannot be below this negative supply, negative 10. So the dV out over dV in is 5 volt, 5 voltage per voltage, the amplification factor. Okay, so that will be all for this first hour. Let's take a break since we have